Let's get started. Hello everyone, this is Korean PS Helper. The topic of this lesson is serial communication. Serial communication is widely used in the field of factory automation. Representative examples include RS-485, RS-422, RS-232C, and MESEC CC-Link. Then, why do we need to use serial communication and what are its advantages and disadvantages? Let's go through them one by one. The first topic we will look at is parallel communication. This is an important concept that must be explained before discussing serial communication. First, look at the diagram. The lines waved from B0 to B7. Parallel communication transmits multiple bits of data simultaneously through multiple communication lines. Because it uses multiple communication lines, data can be transmitted and received at high speed. So, this is parallel communication. However, using multiple communication lines creates several problems. First, at the clock frequency increase, noise and crosstalk are more likely to occur between adjacent communication lines. Example there, here, here, here. In addition, when the number of data bits to be transmitted increase, B8, additional communication lines must be installed. As a result, wiring and maintenance costs increase. Another possible problem is called clock skew. The probability of clock skew increases as the communication lines become longer. Please look at arrow in these diagrams. If the communication lines have different lengths or electrical characteristics, the data bits may arrive at different time. Some data bits may arrive earlier, while others may arrive later. This one is later, this one is earlier. If this timing difference becomes too large, the receiver may interpret the data incorrectly. Therefore, parallel communication is generally suitable for short-distance communications. It is mainly used for applications such as short data buses inside electronic device. In contrast, serial communication is generally uses approximately 2 to 4 wires because it uses pure wires. A basic serial interface transmit pure data bits at one time than a parallel communication. However, serial communication does not transmit multiple data bits simultaneously. As shown in this diagram, it transmits data serially one bit at a time. Therefore, even when more data needs to be transmitted, additional communications lines do not have to be installed. Only needs to increase the length of the transmit data, B8, B9, B10 likely. High-speed communication is important in some factory automation applications. However, in typical serial communication applications, flexibility and expandability can be just as important as communication speed. This is because the communication system must be able to respond to changes such as equipment modifications and additional data requirements. As you can see, there is no communication method that is always better than every other method. There is only a communication method that is most suitable for a particular situation and its requirements. The next slide explains synchronous and asynchronous communication. First, let's look at synchronous communication. Synchronous communication uses a separate clock signal to synchronize the transmitter and the receiver. Data is transmitted and received according to this clock signal. However, in my experience, asynchronous communication is used much more frequently than synchronous communication in factory automation. Therefore, this class will mainly focus on asynchronous communication. Asynchronous communication transmits and receives data without using a separate clock signal. Because there is no separate clock signal, the transmit sends a start bits before transmitting 1 byte of data. Then transmit the data bits sequentially 1 bit at a time. Finally, it sends a stop bit to indicate this end of the data frame. The receiver interprets the data bits between start bit and the stop bits as the actual data. Asynchronous communication can transmit and receive data without a separate synchronization clock. However, the transmitter and receiver must be configured to use the same communication speed. This communication speed setting is called the Baudrate. If the transmit and receiver uses different baud rates, normal communication is not possible. Therefore, the same baud rate must be configured on both the transmitter and the receiver. Let me explain with an example. The waveform I am drawing now is the scale wave generated by transmitter. And next, I will draw scale wave timing used by the receiver. The timing of two scale waves does not match. In the other words, the sampling timing of the transmitter and receiver is misaligned. In the condition, the receiver cannot read the data of correct timing. As a result, normal communication is not possible. Therefore, the transmitter and receiver must be configured with the same baud rate. is correctly. And next slide. The next slide is about UART. UART stands for Universal Asynchronous Receiver and Transmitter. UART is a hardware function used to transmit and receive asynchronous serial communications. UART generally consists of several registers. Here, look at four main registers. The first register is transmit register. Second is receive. Third is the control. Fourth is baud rate setting registers. The characteristics of each register are described on this slide. I recommend pausing the videos for a moment and reading the information on this slide. Okay, let's move on the next slide. I will look at representative electrical standards for serial communications. Discuss three standards. They are RS-232C, RS-422, and RS-485. The first noticeable category is the mode of operation. RS-232C uses single-ended signaling. In contrast, RS-422 and RS-485 use differential signaling. RS-232C is basically used for 1.1 communications. The commonly specified maximum cable length is approximately 50 meters. And standard specifies a maximum data rate of 20 kilobits per second. RS-232C has separated transmit and receive lines. Therefore, it can support full duplex communications. Full duplex communications allowing transmission and reception at the same time. RS-422 can be used to connect one transmitter to multiple receivers. Traditionally, one driver can be connected to as many as 10 receivers. Depending on the operating conditions, the cable lengths can reach approximately 1.2 kilometers. Over short distance, the maximum data rate can reach approximately 10 megabits per second. Finally, RS-485. RS-485 allows multiple transmitters and multiple receivers to be connected to one network. Specification supports up to 32 drivers and 32 receivers. Basic communication distance and speed characteristics are similar of those of RS-422. There is one important point that you must understand. The maximum cable length varies depending on the communication speed and wiring condition. In general, the maximum available cable length decrease as the baud rate increase. Yes, here. Conversely, Lowering the communication speed makes longer distance communication possible. And to explain duplex communication in more details shortly. On this slide, I will explain single-ended signaling. Single-ended signaling uses one signal line. This line is one signal line and a ground reference. This is ground. In the receiver, measure the voltage of the signal line relative to ground. In other words, only one wire carries the actual signal. It then determines the signal status from the measured voltage. Signal lines share one ground. They can be affected by ground potential differences and external noise. Therefore, single-ended signaling can be more vulnerable to noise than differential signaling. Let's look at the waveform. Serial communication ultimately uses digital signal. In other words, the signal repeatedly switches between on and off status. When external noise enters the digital signal line, it can change the signal voltage. Let me add a noise to this waveform. Here. A problem occurs if the noise causes the voltage to cross the receiver decision threshold. The receiver cannot directly determine whether the voltage change was caused by noise or by bandwidth data. As a result, it may interpret the data incorrectly or malfunction. Next, let's look at differential signaling. Unlike single-ended signaling, differential signaling uses two signal lines. This is one signal 1, and this is signal 2 lines. The receiver does not evaluate each signal voltage only relative to ground. Instead, it determines the signal status by measuring the voltage differential between the two signal lines. There is a weight difference. Let's look at the waveform. The two signal lines change in opposite directions. For example, suppose one signal line becomes positive 12 voltages, while the other becomes negative 12 voltages. The receiver calculates the voltage difference between the two signal lines rather than relying on their absolute voltages. Therefore, the differential voltage is calculated as follows. A. The A is V differential equal positive 12 volts minus negative 12 volts equal 24 volts. The receiver determines the data based on the magnitude and polarity of the differential voltages, such as positive 12 volts. Then Y is differential signaling resistance to noise. External noise often enters two closely positioned communication lines with a similar magnitude and polarity. For example, suppose the same positive 3 volts noise is added to both signal lines. If the original signal voltages are V plus equal positive 12 volts, V minus equal negative 12 volts, after the noise is introduced, V plus equal plus positive 12 volt plus positive 3 volts equal positive 15 volts, and volt minus positive 12 volts, modified, minus 12 voltages plus positive 3 voltages equal negative 9 voltages. Although the absolute voltage of each signal line has changed, the voltage difference remains positive 24 volts. Therefore, the receiver is barely affected by the common positive 3 volt noise on both lines. In this way, noise that is common to both signal lines is cancelled during differential receptions. This characteristic is called common mode noise rejection. However, if noise enters only one signal line, the voltage difference between the two lines may change. Therefore, differential signaling does not eliminate all types of noise. It is more resistant to noise than single-ended signaling because it effectively reduces common mode noise that affect both signal lines in a similar manner. Next, let's discuss communication distance. The maximum communication distance of RS485 is not one fixed value. It varies depending on the communication speed and cable type and cable characteristic and wiring environment. As shown in the table, shielded and unshielded cable have different communication distance characteristics. In general, shielded cable helps reduce the effects of external electromagnetic noise. Shielding is especially important near high noise devices such as inverters, servo drivers, and motor cable. In addition, as the communication speed is the baud rate increase, the effects of signal attenuation and waveform distortion become more significant. Therefore, the reliable communication distance becomes shorter as the communication speed increases. The table shows how communication distance changes according to the cable type and communication speed. Okay, now let's move on the next slide. Next, I will explain duplex communication. First, let's look at half duplex communication. In half duplex communication, transmission and reception use the same communication channel, only one channel. Therefore, when one device is transmitting data, the other device cannot transmitting data at the same time. The other device must wait until the first device has finished transmitting. In other words, two-way communication is possible, but simultaneous two-way communication is not. A representative example is two-wire RS485 communication. In contrast, pure duplex communication uses separate channel for transmission and reception. Therefore, while one device is transmitting data, the other can also transmit data at the same time. In other words, transmission and reception can occur simultaneously. Representative example include RS232C and 4 wires RS422 and 485 communications. Next, let's discuss the communication control setting. Earlier, when explaining UART, I briefly introduced the 4 main registers. This time, we will look at the setting associated with the control register. The control setting includes the data bits, parity bits, stop bits, and other communication parameters. When parity is enabled, either odd parity, or even parity can be selected. This setting must match between the master module and the slave module. Master, slave 1, slave 2, or the same parity code. If even one settings is different, normal communication may not be possible. Therefore, each setting must be checked during communication commissioning. The main items to verify are as follows. First, check whether the data length is configured as 7 bits or 8 bits. Data bits 7 or 8. Next, check whether the parity bit is enabled. Parity bit is enabled. If parity is enabled, check whether odd parity or even parity is selected. Finally, check 1 stop bit or 2 stop bits are configured. Stop bits 1 or 2. For example, if one device is configured for 8 data bits and no parity, 8 data bits, no parity, and 1 stop bit, the other device must use exactly the same setting. This configuration is commonly written as 8 and 1. This concludes the basic explanation of serial communication. Serial communication includes many additional applications beyond the topics explained today. Representative examples include Modbus RTU and Multi-Sys-Link. Serial communication is still widely used in factory automation applications. It is used with various devices including PLC, inverter, measuring instruments, temperature controller, and barcode reader. Therefore, I strongly recommend studying its basic principle and communication settings. That is all for today's lessons. Thank you for watching. Have a great day. Bye.